Okay, so yesterday we continued our explorations of conformal field theory and also of ADS-CFT more broadly. And one of the things that we started studying was conformal field theory, a particular conformal field theory, which is n equals 4 super Young-Mills, which is the most relevant one, at least a prototypical example of a theory in ADS-CFT. So in n equals 4 super Young-Mills, we started asking how do we compute the dimensions of operators in n equals 4 super Young-Mills, at least in perturbation theory, which we know is the same as energies of strings in ADS5 times S5, and we also know it's the same as energy of n equals 4 super Young-Mills if I put the theory on a sphere. So it's an interesting quantity to compute. And yesterday we saw that it was also equal, a new equality, which is also equal to the energy of a one-dimensional quantum spin chain. Okay? So before I continue, let me just not fix, but be a bit more precise that in something that often we gloss over because it's really just dimensional analysis, that this delta is a number, right? And these energies have dimensions, right? So what we always mean is energies measured in units of ADS radius. So if I want, this energy is measured in units of ADS radius, so it's 1 over r here or r here. So if I want, I put the ADS radius here. Okay? Not here though. Here it's dimensionless quantity. The eigenvalues of the Hamiltonian that we derived, they are numbers. They don't have any dimension. Okay? But in principle, the ADS radius would be here. Okay. Good. Then we studied what was the idea of relating this to one-dimensional quantum spin chains. It was very simple. We just did usual normalization. So we said that if I take an operator OA and OB, we get log divergences, log lambda, multiplied by a matrix of divergences HAB for different pairs A and B. And then we said, well, but then it means that if I diagonalize this matrix by considering a good linear combination with eigenvalue gamma A of this matrix, this defines a good operator. By good operator, I mean operator which has a definite anomalous dimension. And the anomalous dimension is nothing but the eigenvalue of the matrix. Okay? So all you have to do in a CFT is you take all possible two-point functions, compute the log divergence of the two-point function, don't care about the rest, make a big matrix out of the coefficients of the log divergence, and diagonalize it. Okay? So that's the prescription. This operator you see now, this scalar operator that we started, this was a product of L scalars, so this has dimension L. But I multiply it by something with dimensions to the power gamma. So of course now the dimension of this object has to be L plus gamma, right? Just by dimensions, okay? So, okay, so now this is what's called a quantum correction or an anomalous dimension. People sometimes call this anomalous or quantum dimension. It's generated by a quantum effect. We also saw that we could think, if we want, why not, of this operator's trace of product of scalars as a cat in an SO6 spin chain Hilbert space, because it's just a question of notation. And in this language, this matrix turns into a nearest neighbor spin chain Hamiltonian with SO6 symmetry, so which is a linear combination of permutation, trace, and identity. And then we saw that quite remarkably, the ratio of the coefficient of the permutation and the trace were exactly such that the theory would be exactly solvable and that I could compute these energies exactly, even though I did not explain in the slightest how I would do it. Okay? We did not compute this coefficient -2, of course, yesterday because it would involve many diagonal terms, but I'm quoting the result here, it's -2. Okay? So, before we move on, I would like to make a few comments about how generally we expect this thing to hold. So how often do we expect that we can trade a problem in 4 dimensions, computing the dimensions of 4-dimensional operators, to computing the dimensions of 1-dimensional quantum spin chains? And the answer is roughly always. Because we really use nothing. We just use planarity. So why is it nearest neighbor? Why can we map it as a spin chain? That's just notation. From the planar limit, if you have a trace, you can think of it as a cat. So there's nothing deep there. Why is it a nearest neighbor Hamiltonian, which is the kind of Hamiltonians we like, because they are like the ones that appear in real systems, which are local? Well, this is just the planar limit. I cannot draw graphs that pass the lines pass by each other. So whatever I would compute, it has to be a nearest neighbor Hamiltonian. Why is it a nice combination of permutation, trace, and identity? Well, this had to be just SO6 symmetry. There are no other invariant tensors you can write. It's the only reasonable delta functions. So really the only surprise, the only thing I could have gone directly here from the beginning, the only subtlety is the ratio being -2. So it's the only thing, is the fact that it's integrable, that it's exactly solvable. But the fact that I could map it to a one-dimensional spin chain, this of course is totally general. I can always do it. Okay? And then this was quite remarkable. It means that the theory is integrable. People then went to string theory, which is the regime that dominates when the coupling is large. This is where we have classical strings. And here is where we have perturbative Young-Mills, right? And you could go to classical strings, and people studied and saw that they found integrability there as well. And they predicted the spectrum of strings. They predicted a bunch of spectrum here. And beautifully, what you see is the emergence of strings from a gauge field. You start computing the dimensions. They start with some classical value L plus some slope, which is the one loop anomalous dimension that we computed. This tells us how it starts here. And then it goes up and diverges and goes to match exactly the spectrum of string theory that you would have predicted. So I think it's really quite a beautiful thing. You predict something about classical strings, now you forget about it, go here, compute the spectrum, see where it goes, and it goes beautifully match the spectrum of classical strings. Okay? What happens, what I told you as well, is that there is a big gap between most of the states which become heavy, because most of the states correspond to massive string states, right? That's the majority of them. And then there is still a lot, but a measure 0 of them, which are supergravity states, which are the graviton and its super friends and the 10-dimensional graviton that stay at with some energy of order 1. Okay, some lines of order 1. They are not all the same. There are a few, but they stay of order 1. Okay. For example, here you can easily see that because of these combinations, that if your state is symmetric and traceless, if it's symmetric, it's cancelled by permutation and minus identity, because permutation minus identity antisymmetrizes. And if it's traceless, it's killed by K. So if you take any trace that is symmetric and traceless with respect to all the indices of the scalars, right, you get a 0 energy state if you act with a Hamiltonian. Okay? This could be a coincidence at one loop, but it's not. It's really a consequence of supersymmetry, in fact, that if you take a state with scalar which is symmetric and traceless, it has to have 0 anomalous dimensions. So this fact that this is -2, I don't need to compute. I can just compute this diagram that we computed yesterday, and then I know it must be -2 because it must kill symmetric traceless states. So then I really don't need to do any Feynman diagram computation. And then those states that are symmetric traceless, for example, are examples of these states that stay here. But of course, most cats that you write are not symmetric traceless. The majority of them would go up. Okay? Okay, now before we move on, there was a typo that I did something which was, there was a small typo that no one noticed. At some point I said that crossing symmetry says that f of zz bar equal f of 1 minus z1 minus z bar, right? And there was a power of cross ratio missing. Because what you have is that the 4-point function, I can freely flip x2 and x4. That's not a problem, and I should get an invariance. But the 4-point function is a factor of cross ratios that I chose times a function of zz bar. The function of zz bar, z goes to 1 minus z bar goes to 1 minus z bar. But the prefactor changes as well. And if I factor out the prefactor, the ratio that I get is a cross ratio to some power. Is it clear? You see? So I add this prefactor, 1 over x1 minus x2 to the power 2 delta, x3 minus x4 to the power 2 delta, times a function of z and z bar. This must be equal to the same thing where I replace 2 and 4. This tells me that this function is equal to the other one with 1 minus z bar up to the ratio of this over this with this change, which is a cross ratio to some simple power. Okay? So that factor was missing, this cross ratio to a simple power. And then, when I was separating contribution of the identity to the rest, I said at some point, this guy is 1, because the 3-point function with identity is just a 2-point function. That's correct. But I also said this factor is 1, but it's not 1, of course. This factor is what I get when I subtract this minus this for the identity. So it's 1 for this channel, but the other one, from the other channel, there is again this cross ratio to some power. So what replaces the 1 that I said is 1 minus cross ratio to some power. Okay? Anyway. The conclusions are, of course, all the same. It is just a small typo. Any questions so far? Okay. So let's move now to the topic of Wilson loops and Wilson lines. There are also very interesting observables in gauge theories, as I will now explain. And they are another beautiful example where we see this emergence of strings from gravitons in a very geometrical way. Okay? So yesterday, I told you very briefly that if we want to describe the propagation of a, now I will put here a rectangle and I will fill this, of a classical particle in the presence of the propagation of a quantum particle in the presence of a classical gauge field, right? So if we say that this is quantum and this is classical, okay? We saw that the propagation from one point to the other, y, would be described by some path integral. So if the particle is quantum, I must sum over all paths gamma in x. I weight them by e to the minus the mass times the length of the path, which is the integral of square root of x dot square. And then there is a classical gauge field which is given by the Wilson line along the path gamma, the path order exponential of the gauge field along gamma of A. Okay? Good. Now, if we consider still a quantum particle, but also a quantum gauge field, so one that fluctuates, right? So I also don't specify what the gauge field is, but let's sum over all configurations of gauge field. I just want to point out something obvious. All I would do is I would say that my propagation would now be described by an integral dx e to the minus mass times the length times the expectation value of the Wilson line, right? Where I average over all possible gauge fields. And there is yet another thing that we could try to think about. We could think, what about the case where my particle is classical? So say it's some classical probe, some heavy particle that I put in my system as a probe of my system. And the gauge field here would be quantum. Okay? And in this case, the correct this way of describing the interaction of a classical with a quantum Wilson loop would be just to compute the expectation value of gamma. Okay? And I would not sum over paths. Okay? If you want, you can still e to the minus m times the length of gamma. I mean, if you want, and this is your choice. Okay. Now it depends on the definition. You define it if you want. You can put this, it's a number, you can multiply it. But what's interesting is just the Wilson loop. Okay? So let's think of an example of this, putting some classical particles and considering the gauge field to be quantum by imagining that I put some heavy quark. So I put some quark and some antiquark. And I would like to consider the quark-antiquark potential to measure the force between the quark and the antiquark. So I want to see what is the energy of this configuration as a function of R to tell me what's the attraction between the quark and the antiquark. But I don't want to let the quark and antiquark move quantum mechanically. I want to fix them at some distance R and study the energy of this configuration. So this, I want to study e to the minus. So I put it in some large time to project into the ground state. So I want to say e to the minus beta. And then I say the energy without the quark-antiquark plus the energy because of the quark-antiquark. If I would like, say, to divide by just the ground state energy of my quantum field theory, what is this? Well, this is just exactly what the Euclidean path integral computes, right? So I'm considering the path integral, e to the minus my action, that could depend on the gauge field and matter and so on. And then I add the probe plus the integral of j mu a mu, where we will describe this probe that describes the quark and the antiquark, and I would divide by the same thing without the probe. Right? Because this computes what's the ground state energy of this system with a probe over the ground state energy of the system without the probe. This way I cancel this zero and I access directly V of R. So what source do we want to put? Well, we want to put our quark whose position x is what? It moves in time and then it's at some position 0, 0, 0. And here a quark that is at some time, at some separation, say R, and standing quietly. So what this J would be the quark would be static, so J mu would be something like saying that I have some static quark. It's located at the origin, and then I have the antiquark, which would be static and located at x minus R times some unit vector at some other position. Okay? And so you see that when you compute this source, you can think that what this interaction is the integral over the union of two contours, gamma 1 union with gamma 2, okay, of A mu of x of t x dot mu of t dt, where what are these contours? One contour is x mu equal to t 0, 0, 0. This would be gamma 1. And gamma 2 would be x mu equal, this is one parameterization of going minus t r 0. Okay, or, okay, yeah. Okay. So if you take derivative, it's just delta phi, this is just this Kronecker delta, and then it will just put me. In other words, the way I would picture this is by saying that, well, it's that picture there. This is gamma 1, and this is gamma 2. And now to make it nicer, what we can do, since nothing special happens here at plus and minus infinity, we can, to make it more gauge invariant, we close it here and here. Right? So this should probably be better defined. We don't know very well what to do at plus infinity, but this now makes it into a closed Wilson loop with totally gauge invariant, right? This beta is much bigger than this R. It's a very stretched rectangle, I remind you. So we just put some caps to make everything kosher, right? Just to cut it such that it will be gauge invariant. As we saw, the Wilson loop is a totally gauge invariant quantity, whereas Wilson lines, they still have a bit of gauge covariance because of the endpoints, and it's nicer to close them up. Okay? We close it, and then as we close it, so we add this union of the two caps at the top and bottom. But then what we conclude is that this is nothing but the expectation value of the Wilson loop associated to what contour to a thin rectangle of size beta by r. Okay? In other words, if we want to summarize, we conclude that the quark-antiquark potential is equal to the limit when beta goes to infinity of minus 1 over beta log of the expectation value of the Wilson loop associated to a rectangle whose size is beta times r. Okay, which is an example of this problem here. Yes?
Could you please just elaborate to a little more detail how from the path integral, where do you get the Wilson loop there? Like in particular where the path order exponential comes from? Like how do you get from time ordered path integral to like I see the formal similarities, but it's just not clear to me.
So you are saying, how do I see that exactly the way of coupling that I should order them along the path, right?
Yeah, for example.
Well, if you would rederive in the usual way when you derive a path integral, in the same way that we say that things should be time ordered, right? So you would follow, I mean, after all, this is just a particular case of what we derived before. Why was it a Wilson loop here, right? Because we had to follow the path of the particle and resolve the identity and insert the path everywhere. This and this are just particular cases of each other, right? If you have a very, very, very classic big particle, right, you can force, I mean, there's nothing special between this and this. If you bought this here, this derivation of why it is a Wilson loop, here I'm just being sloppier but doing the same thing that we did slower to derive why the Wilson loop was this. But what else can I tell you? Let's see. Okay, yeah, I agree that here I was not very careful with the color indices of the gauge field, and it looks more like some derivation that would hold, say, for QED, for example, without any problem. But for QCD, you are a bit worried where are the traces and so on. Indeed, I would have to do it a bit more careful if I would like to put all the indices there. But of course, this is the only reasonable conclusion, and it's the correct one. If you want, at the end, we can discuss more where the color indices would go in all detail. Okay, so let's, as an exercise, think about this Wilson loop that is out. This is a particular case of this description here, and let's rederive what happens when I have. Let's rederive the interaction between two electrons, or between an electron and a positron. Let's think of the Coulomb interaction as a particular case. Okay? Okay. So, okay. So I'd like to make a few observations. So first of all, in QED, right? Or maybe not yet in QED, sorry. In perturbation theory, what did I say? In perturbation theory, we have that the way to compute this Wilson loop is by writing that, well, it starts with 1, as you saw in the tutorial, plus, now the expectation value, so the expectation value of the Wilson loop is 1 plus the expectation value of an integral of a single gauge field. But the expectation value of a gauge field would be 0, so we need 2 gauge fields at least. So what we would get is the integral, right, a double integral of the expectation value of 2 gauge fields plus higher point function, which, as you did carefully in the tutorial, gives the integral dt1, dt2. Well, there might be some coupling, lambda in general, and then the derivative at point 1, x dot at t1, dotted with the velocity at point 2, divided by the square of the separation at the 2 points, x of t1 minus x of t2 squared. So in pictures, I have some Wilson loop, and I consider an exchange between a point at time t1 and t2, and I integrate over the endpoints, plus dot, dot, dot. Now, in this dot, 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 I have, in QCD, say, or in pure chromodynamics, I have complicated stuff like interactions between the gluons, etc. But in QED, when I just have photons that don't interact with each other, and I also have diagrams like this, right? But in QED, when the photons don't interact with each other, these diagrams are not there, and this one, it are just a square of the diagram at one loop. Why are they the square? Because I remind you that there is a big difference in QED and QCD. In QED, these photons can be everywhere. There's no such thing as planar limit. The lines can cross or not cross. They are invisible to each other. And this diagram is just a square of this one, therefore. So in QED, what we get in a free theory, in a free abelian theory, this becomes just the exponential of the one loop result. And this is an exact result. So in QED, you can just compute exactly. Just compute the one loop integral and you exponentiate it. And this is what we have to do if we want to study the quark-antiquark potential for an electron and a positron. So what we have to do in QED here is study exactly this one loop diagram, right? Okay, so this is what we are going to do, therefore. Okay, so our potential V of R would be 1 over beta times this diagram here, right? Now, this diagram here, there are many possibilities that I could compute. There are many many possible diagrams depending on where this endpoint is and where this endpoint is. Right? So we have to compute a few diagrams. So this splits into a bunch of diagrams, okay? We have this case that I drew, but we also have this kind of diagram, and we also have this kind of diagram, and also this kind of diagram, and also what? I think I did all of them, no? No, and also this kind of diagram. Okay? Okay. So, okay. So let's analyze all of them in detail. So this one is the simplest. Can someone tell me what this diagram gives? Zero, because the velocities are orthogonal, right? X dot dot x dot, they are just orthogonal. So this is it, which is good. We said adding these caps should not be anything very significant. If we would start getting important contributions from the caps exactly, it will be kind of weird. Okay, good. This one is zero because of orthogonality, because the gluons are just orthogonal. So what about, now more interesting, let's see about this diagram here, say. Okay. So this one here. This one here, let's write it explicitly. So we can write that I integrate from minus, say, beta over 2 to beta over 2. Integral from minus beta over 2 to beta over 2. And now I'm choosing a parameterization where my parameter of my curve is the height itself. Okay, that's why I'm going from minus beta over 2 to beta over 2. Why didn't I choose another parameterization? I could, but it doesn't matter, remember? This is parameterization invariant. I can choose indeed other parameterizations, but this one is a nice one. In this one, the velocities, because the distance I choose is the position itself, the velocities just give 1. And then what's the distance between 2 points here? Well, it's just Pythagoras, right? So it is just the distance between the two, which is r squared, plus the distance x minus y squared, and I integrate dx dy. Right? And I want to study this integral when beta is very large. So when beta is very large, you see what happens, that this diagram is when beta is very large, so I can integrate over the difference and the sum. Right? So if I integrate over the sum doesn't appear, so I get a factor of beta. And if I integrate over the difference, I get 1 over r times something, I don't know, it's probably some pi or 1 over pi or whatever. Some number. Right? So what do I get? I get beta over r times some number that I don't care. I mean, of course I care, but you should compute. Okay? So this diagram gave me beta times some number over r. Which is good, because we want to divide by beta and take the limit when beta goes to infinity, and this has a good limit, which is 1 over r. Okay? So we are already recovering what we want. We see that the potential between the two is 1 over r, which is, of course, the Coulomb interaction between the electron and the positron. So that's good. Okay? But I'll collect everything together, but for now, I would like to discuss the other diagram. So first, this one here is irrelevant as beta goes to infinity. Again, once more, reinforcing our idea that the caps should be doing nothing special, because it doesn't scale with beta. I integrate in a small distance r, so it definitely does not scale. In fact, it's terrible. I mean, it decays with beta because it propagates for a huge distance, and then I integrate it over a small amount. So this is super irrelevant when beta is large. And we are left with these diagrams here now, which are when the endpoints are at the same position. Okay? And when the endpoints are in the same position, I just go here and replace r by 0. It's the same thing with r equal to 0. Now, if r was 0, this diagram would not be convergent. It would diverge. Right? So there would be a divergence. So the diagrams with the same, which end on the same one, they will diverge. So I would have to put a cutoff, say epsilon, and they will diverge like 1 over epsilon, because I'm integrating 1 over x minus y squared. So if I integrate and I put a cutoff of how far the operators can be, there is a 1 over epsilon. Right? And then, you see, I'm even going to give you the result of these diagrams for a general contour, like Mickey Mouse, not necessarily a rectangle. Okay? This kind of contribution gives a divergence, which is 1 over epsilon. That can happen at any position along the loop. Right? Do you agree? So it is just 1 over epsilon times the length of the Wilson loop. Okay? And you can see it explicitly here. If you integrate this, it gives 1 over epsilon, right? And then it happens in any beta. And in any beta here, any beta here, any beta here, any beta here. Okay? So, okay. So we conclude that this computation here in QED gives a number over r, right? And then the length is proportional to beta, so it also gives some constant over epsilon. Okay? So this is what we get for our quark-antiquark potential in QED, which means the Coulomb interaction between two electrons, or an electron and a positron. Okay? So this is our Coulomb, our potential. So now let's make a few comments on this on our results. So here is the summary. Okay. So the first comment is that if I want to study the force between the two particles, I don't care about this term, because this is a constant. If I take derivative with respect to the radius, if I study variations, I don't care about it. It's like a constant shift of my energy. Why would I care? Right? So if I want to study the force, the constant over epsilon is irrelevant. And then I get 1 over r squared, the usual force between two electrons. That's the first comment. But the second comment is that it's actually nice, and it actually makes sense that we find such divergence proportional to the length. Because the only thing it is telling us is that when a particle interacts with a quantum gauge field, what you thought was the bare mass of the particle now gets renormalized. So all it is doing is shifting what you thought was the mass to a new quantity. So all you do is you call the mass you had before plus this divergence times delta m, and you say this is actually the renormalized mass. So the divergence, in fact, can be thought of as mass renormalization. It is just the effect that because the particle interacts with the gauge field, effectively, if I were to take its bare mass, it would receive a big contribution from this effect, and in fact what I measure is just a renormalized mass, and there is no problem with it. It's not physically observable if I compute the force, but it also has some nice interpretation, and it's not unexpected that I should find such effect. Okay? Okay, good. So yeah. So in n equals 4 super Yang Mills, the potential now between the potential would be now 1 over r, because it's a conformal theory, so there's nothing else I can write. But now there would be a function of lambda, a non-trivial function of lambda that's not just a number, that comes from resumming all possible Feynman diagrams, and which is something a priori complicated. Okay? And in QCD, the potential would grow with distance, indicating that the theory is confining. So people would study this Wilson loop, say, in the lattice to measure the anti-quark potential and to see that it confines and measure the string tension and so on. Yes?
In case of n equals 4 super Young Mills, we would have a diagram like this interacting between the two
yes.
But even with that interaction, like how do we get the, is there a good pictorial way to understand how we get CFT from it?
Why we get just 1 over r?
Yeah.
So the reason we get just 1 over r is because of dimensional analysis, because this has the right dimensions and you have no scale. So the only scale in your problem is the separation between the two quarks. There's no other scale, so this is the only thing you can run. So it had to be the case. But you are right that in n equals 4 super Yang Mills, the diagrams that contribute are all these gluon graphs between the two, right? Which are very, very non-trivial, and which, as we said, draw some sort of string, and some kind of string picture emerges, at strong coupling, say, and then this alpha of lambda is something you have to really compute from. You start at weak coupling, it's only this diagram. And then, as you compute more and more and more diagrams, it becomes more and more complicated. And it's a non-trivial function of lambda. So at one loop, it's roughly what we computed. There's no difference between QED and n equals 4. But at higher loops, of course, there is a difference. Okay? So this function here, alpha of lambda, starts with some slope, a number, which is, of course, well computed, times lambda. I think this number is 1 over 2 pi or something like that. So it starts like this. And then, at some point, it should be described by classical strings. Do you agree? Okay. So now, so as you see, Wilson loops appear more or less everywhere when you study particles moving in with chromodynamic gauge fields. in fact, there are many other reasons why people like Wilson loops and Wilson lines. They are very useful if you want to describe non-local observables and take, say, a quark and an anti-quark, and you want to consider, say, some physical quantity that describes a quark at some position x and an anti-quark at some position y. A priori, this is not gauge invariant. I cannot just multiply these two operators. Of course, if I unite them by a Wilson line, I get something which is well defined. Because the quark transformed by gauge transformation, the Wilson line by 2 gauge transformations, the anti-quark by 1, and in total, this is a totally good quantity. So it's a way of allowing us to make sense of stretching and separating our objects. And also, even when you have Wilson lines and you start considering small deformations of Wilson lines, the small deformations of the Wilson line, they induce some correction to the Wilson line, some delta Wilson line, which is related to the field strength of your problem times the small area element that is in this plane. So you can even define local operators and obtain local operators by shrinking and considering deformations of Wilson loops. So they are more general than local operators. You can then go and reproduce local gauge invariant operators like the field strength and so on by considering deformations and small deformations of these Wilson loops. So the law is that if you could describe Wilson loops in a quantum gauge theory, that in principle it contains the information about roughly all physical observables in the gauge theory. So what is their interpretation in terms of string theory, if we start from our original point of view? Remember that we thought that I could think of this as endpoints of my open string. I could think that this will describe an open string, and this will describe some surface right here that appears between this open string. Okay? So let's try to think of what could be the description of a Wilson loop, what could be the ADS-CFT prescription for computing these Wilson loops. Okay? So for that, it's convenient to go back to our original picture of the decoupling argument and think there what it could correspond to putting a classical particle interacting with a stack of branes. So we had our stack of branes, many, many branes, right? And this is n equals 4 super Young-Mills, which has many massless open strings here attached to these branes and so on. And now I want to put a heavy particle interacting with this stack of branes and move this heavy particle along some path of my choice. So how could I put a very heavy particle on this? Well, what I can do is I take one of the branes and split it and put the brane here. Okay? Where this would be far away, so it would be at the distance r far away from the brane. Okay? So, which means, in terms of Poincare, be careful, z very small. And I put this brane and consider an open string that stretches from this brane to this brane. This now describes a very heavy excitation. Okay, it's stretched, so it's a very heavy excitation. So what should I do? This is my probe. And now I take this heavy probe and carry this probe along some contour that I choose. I carry this probe and some contour gamma. Right? And what will it describe? Well, it will describe some interaction of this probe with my brane, with many possible closed strings popping out and many possible string processes happening up here. Right? But the process that happen up here, I know that I can replace them by the background, by the ADS5 times S5 background. So, okay, so here lots of things happening, but we know that in exchange we can erase all the branes and just put the background. So what do we conclude? We replace this, we erase this, and put here ADS5. And then you see that here at z much smaller than 1, which is the boundary of ADS5, we should put some local, we should let the string end there. Right? So the conclusion is, the prescription, the proposal, is then consider the boundary of ADS, because the boundary of ADS was what was before z very small. Consider a contour that is on the boundary of ADS, which is our contour gamma. And now consider all strings that end on this contour, and consider the path integral over all possible string surfaces with these boundary conditions that must end on this contour on the boundary of ADS. Okay? And inside they do whatever they want. We should sum over all the possibilities, and they move in ADS, and which mimics the interaction, their interaction with the branes. Okay? Any question here? So in principle, if you were powerful enough, all you have to do is consider, therefore, an open string partition function where you sum over all string solutions that end on a given contour, and that should give you the expectation value of a Wilson loop in n equals 4 super Young-Mills. Okay? Okay? So this is the proposal. This is equal to the expectation value of the Wilson loop associated to that same contour. Let me try to draw the same contour. To the same contour gamma. Okay? So this is the proposal for the map. Now this side here, as we saw, is easy for very small lambda because it's perturbative. We do like a one loop diagram like what we did. Right? If we are feeling very motivated, we might try to do one more loop, and indeed people did maybe one or two more. Right? It's a little bit more work. Now we have to see these interactions and so on. But this one here would be easy for when the string tension is very large. Because if the string tension is very large, I remind you that each of these configurations is weighted by e to the minus the string tension, which ends up being written as square root lambda over 2 pi, times the area of my minimal string, the action, which is just the area of my minimal string. And when the lambda is very large, this will become just e to the minus square root lambda over 2 pi times the area of the minimal surface that ends in this particular surface. Right? And therefore, my quark-antiquark potential would become given by minus 1 over beta times the area of a minimal surface that ends on a rectangle in the boundary of ADS. Okay, very, very good picture. Okay. This is the boundary of ADS. This is a big rectangle of size beta by r. And if you see, you take the log and so on. So if you compute the area of this big rectangle, you get the quark-antiquark potential. Yes?
Why is the minimal area not just the area of the rectangle? Is it because of the ADS metric?
That's because of the ADS metric. In fact, the string wants to get away from the boundary as quick as possible because there is 1 over z squared. So in fact, it's even worse than that, because the area of a small slice here, this area here, where this thing is epsilon here, this slice here, it's infinite already. It costs infinitely many area, because at this epsilon, the metric is 1 over epsilon squared times, so this area of this strip is roughly 1 over epsilon times the length of the curve, right, as we see here. Okay? So that costs a lot of area because of this rep factor of ADS. So in fact, what happens is that this area is divergent, and you should regularize it by subtracting some epsilon divergence, which you can think that it's the area of the surface that starts here and just goes vertical away from infinity, as you will see in today's tutorial. And this regularization, is it something surprising and so on? No, it's the same. We also see it in field theory. And we should think of it as just some renormalization of the Wilson loop that we should do anyway, which is there, which you can think as renormalizing the mass of this probe. Okay? And remember that also when we were studying these geodesics, we also saw that the length of the geodesic, strictly speaking, is infinite. So when we compute this two-point function of two geodesics, it was diverging with epsilon to some power. We define renormalized operators by again absorbing that epsilon. And once you do it, then 3- and 4-point functions and so on were finite. Here as well, whenever we compute the Wilson loop, we subtract out this simple divergence, which is there, but which is very simple. It's 1 over epsilon times the length of the Wilson loop times some number. Okay? Now this area now was computed, and you are going to compute it in the tutorial. It's square root lambda times some complicated number. Okay? Some gamma to the 1/4 to some funny powers and so on. It's there, you have this minimal surface. So it's about computing areas of minimal surfaces in ADS. And therefore, we conclude that the area of our minimal string, it starts at lambda, and it goes here to square root of lambda, and it's some curve in the middle. That actually, using again integrability results, was plotted a few weeks ago to study this interpolation between these 2 points by Gromov and friends. Based on some equations that Amit Sever, Juan Maldacena, and Diego Correa had written a few years ago, and they were on hold, and even though the integral equations were written, only a few weeks ago, as I said, or maybe a few months ago, people managed to solve them and plot the intermediate curve. And it's another beautiful example where you see the gluon regime, and then you start increasing the coupling, and you start getting something that has an interpretation as an area of a minimal surface. So now it's this ontological, blah, blah. Of course, you can now say whatever words you want, but in practice what we see is that we start in 4-dimensional world with gluons moving in 4 dimensions and giving us Coulomb law with the coefficient that we expect from 4 dimensions and so on. And our description is just a gluon going from one point to the other through 4 dimensions. But as we take out the coupling, we start getting square root of lambda, which is the string tension, times a bunch of very, very funny factors, whose only reasonable explanation is as an area of a minimal surface in ADS. So it's really as if an holographic direction emerges, and it becomes a good description only, of course, when lambda is very large. But it's another example of gluons becoming strings, and where we can follow them and try to understand dynamically what is going on. Okay? Any question here? So I think this is enough motivation for the tutorial. And in the remaining minutes, I would just like to comment on a slightly more advanced topic, motivated by some questions that some of you asked in the first week, which was whether there would be any chance of looking at these large N diagrams and trying to derive what the string theory is. Right? We started with this large N, and we said, well, this large N diagram, they look like a string because there are some cartoon and they become dense. So this should be a string and so on. But in practice, it's tough. It's not like you can start from the diagrams, do a bunch of manipulations, and get a string. So I want to tell you about some recent development where I think perhaps it could be the right playground to try to make progress in this direction. This is more speculative now. Okay? Okay. So you see that when you have a quantum spin chain here, and an integrable quantum spin chain, a natural question is, well, when I have a quantum spin chain in condensed matter, there are many things I can do to it as an experimentalist. For example, I can turn on a magnetic field. If I turn on a magnetic field, in fact, for example, this spin chain would not lose its integrability. In fact, turning on a magnetic field, all it does, in this case, if I turn it appropriately, is tell me that as my excitations of my quantum spin chain, my magnets, they go around, after they go around, they pick a phase, some Haranon-Boff phase, like we saw in the Wilson loop story. When a particle goes around a solenoid with a magnetic field, it picks some phase, like we saw in this Wilson loop business. So we could imagining what happens if I take this periodic spin chain and start changing the boundary conditions such that I twist the theory a little bit in the way of thinking in my mind that I'm roughly putting this magnetic field. Right? So this is very natural from this point of view. So then you can ask, is there a deformation of n equals 4 super Young-Mills? which corresponds to this minor modification, where I can put some magnetic field. In fact, it's more than a magnetic field, because you see, this theory has various types of excitations. It's not an SU2 spin chain, it's an SO6. So I can put roughly a magnetic field associated to each of the cartons of my group, right? So I can put a magnetic field that measures the various colors, or chemical potential if you want, that tells me as particles of different kind go around the spin chain, they pick a different phase, okay? So indeed, there exists a deformation of n equals 4 super Young-Mills, whose net effect is to preserve integrability, but to introduce such twists, to twist the boundary conditions and to introduce such magnetic fields. So this is what's called some gamma deformation of n equals 4, which is a very minor thing, as I said. So if you think locally, you have your spin chain with some excitations moving around and scattering. The local physics is the same. It's just a global thing that as the excitations go around, they have to pick some extra phase, a minor thing. This deformation, however, if you think a little bit what it does, if you start analyzing, for example, it does things of the sort that what was before a commutator of scalars, for example, minus phi 2, phi 1. Now, after you twist and you introduce these parameters, you get stuff like e to the I gamma, e to the minus I gamma. So it's some kind of non-commutative structure that you look at things that before came with the same coefficient and you start twisting them around. And if we normalize the kinetic term to 1, which is something that typically I have not been doing, but let me do it now, there would be some G Young-Mills square multiplying these two terms, plus a bunch of other stuff. Okay? Now, so this is a nice deformation that you can do. It was actually first identified at strong coupling as being, people saw that at strong coupling there is a way of changing the boundary conditions in the sphere by doing a sequence of transformations in string theory known as T-duality, some S-shift, and then another T-duality. So these are some symmetries of string theory. And these symmetries of string theory hinted at the possibility of changing the boundary conditions in the sphere, and then people went back to n equals 4 and started studying what deformations of n equals 4 could I do that preserve normalizability, conformality, integrability, and so on. And they found some family of deformations with 3 parameters, gamma, that you can do, and here I'm writing one of the parameters, okay? Okay, so as I deform n equals 4, so I have a bunch of terms, and I start adding these deformations with some real gammas, the theory is unitary, and everything is more or less okay. Conformality is slightly broken, but so for very specific observables, so I don't want to discuss it, but everything is good. And then recently, like perhaps a month or two ago, Kazakov and his collaborator proposed a funny limit, which is, why don't we take these twists and make these twists imaginary? Okay? So let's make some kind of imaginary magnetic field. Why? Why would you do such crazy thing? Well, because they pointed out that, well, when we put something imaginary, there's something we lose. Well, I mean, perhaps sometimes we lose, sometimes it's a bug, sometimes it's a feature. The first thing we immediately lose when we start putting complex stuff where we shouldn't is unitarity. Things that were real and unitary. Okay, indeed, this is not going to be a unitary theory. Okay, so if you like unitary theories, you should forget everything I'm saying. But sometimes you like non-unitary theories. In statistical mechanics and so on, there are often many examples where we are interested in non-unitary theories. But their observation was, wait, if I put this twist to be imaginary, and then if I put it to be very big, this term is much more important than this term. So they proposed the following limit. Let's take this twist fixed, this combination fixed, when the coupling goes to 0 and the magnetic field goes to I infinity. Okay? So this is a very funny example because I wrote plus dot 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 and plus dot dot dot, but I don't need to because this is the only term that survives. No other term survives. So in this limit, n equals 4 super Young-Mills, when we take this limit, there are a family of such limits you can take, but I'm taking the simplest ones. But now the action of n equals 4 super Young-Mills becomes literally just the following. It becomes integral of d phi 1, this is one of the scalars, d phi 1 dagger, plus d phi 2 dagger, Okay, so this is what we had before. So we had, now I'm using a slightly different notation. So instead of using phi 1 up to phi 6, I'm going to phi 1 plus I phi 2, which I'm calling phi 1. So let me put some, I'm using what's called SU3 notation. Phi 3 plus I phi 4, which I'm called phi 2, and phi 4 plus I phi 5, which I call phi 3. Okay? So then this is what I get. And then out of the commutator, only that term survives. So I call this coupling psi square, where psi square is the G Young-Mills coupling square, times e to the I gamma. Okay? This was not ideal. I did a mistake here. 1 second. Okay. Okay, so I want to multiply and divide by n. It does nothing. So what the limit we want to take, there's still a good planar limit. Perturbation theory is still the planar limit. So it's this full combination that I held fixed, right? So if this is what I call. So I should put, if I want to write it in this form, just with the analog of a 't Hooft coupling, I should put a 1 over n. But this is just to have a good n limit. And then out of the commutator square, only one term survives, which is phi 1, phi 2, phi 1 dagger, phi 2 dagger. This is the full action. There's nothing else. This is the action. Which is familiar because it was the action that I told you to have a look in the first tutorial, right? Which was a non-unitary matrix theory where you have two fields, phi 1 and phi 2, and phi 1 dagger and phi 2 dagger, right? And this is the full action of n equals 4. So what we see here is kind of fun, which is that gluons and fermions decouple. So if we take the coupling to 0, we will get free fermions plus free gluons plus free bosons, right? But in this limit where we scale, the scalars still interact a little bit. I still get some interacting fermions, scalars, sorry. But the fermions and gluons just dropped out. So strictly speaking, it's no longer a supersymmetric theory. It's not even a gauge theory, strictly speaking, because the gluons just went away. Even though probably I should only consider singlets in this theory, but there are no more gluons anymore. There are no more fermions. It is just a theory of two, non-unitary theory of two complex scalars. Okay? Now, in this theory, however, if you start doing perturbation theory in this theory, as we saw, for example, when we study the correlation function of, say, two phi 1 to the L operators, which I draw as this kind of melon or cylinder, if I do it with coupling, say, so this would be phi 1 to the L, and here phi 1 dagger to the L, right? We saw that in this example, actually, the diagrams that can contribute to this two-point function, there are not that many. In fact, the only possibility is to have a phi 2 that wraps around once, or 2, or 3 times, or 4 times, and so on. These are the only possibilities, because the only orientations possible is the one where phi 2 enters phi 1 from the right. So these are the only diagrams, for example, that would contribute to this two-point function. So it's a very restricted class of diagrams. They still look like a discretization of a string going from a point to the other. But what a beautiful discretization it is, just a square lattice and so on. So I do think that perhaps in this theory, where things are indeed this simple, they are not trivial, but they are indeed much simpler than what we could expect, there is the question of whether we can understand here the origin of strings, the origin of integrability, and the emergence of strings for gluons in a theory which which does have many funny features that are yet to be understood concerning what could be the string dual of such theory in this extreme limit. And this is one of the topics that people are trying to think of right now. So I think I will conclude now. So in these last lectures, I tried to touch upon a few fields that were studied very recently and that are still the topic of investigation, to give you a flavor of the kind of things that people are doing within ADS-CFT. ADS-CFT is a huge field. This field of gauge gravity dualities is huge. I mean, I think it occupies roughly half of string theory. It's in a way or another, either directly or tangentially. So it's really a huge field. I mean, the original paper of Juan, has like 20,000 or 10,000, or some crazy number of citations. It's absolutely humongous. So I could only tell you a little bit about a couple of things of ADS-CFT. We did not discuss black holes at all, for example, but Freddie will probably mention some in his lectures. But I hope you got a feeling that these dualities are promising not only in helping us understand quantum gravity and as being a definition of quantum gravity and a way of understanding quantum gravity as starting from quantum field theory, which is something we understand much better, but that by studying these dualities, by trying to solve these theories and to compute things both in string theory and in gauge theory, we are learning a ton of very exciting things about quantum field theory, some things that we could have discovered many, many years ago. But now with ADS-CFT as a guide, it really helps often to give us hints of kind of cool things that we could explore. And it really, I think, has boosted our understanding of quantum field theory. So to conclude, let me allow just to spend 1 minute just giving you one advice now that you're going to do your PhD and so on, which is some very simple advice, which is when you pick a topic for your PhD, pick something that looks huge and intimidating. I don't know if I told you already, but don't go for something that in one afternoon you understand the boundary of the field and you feel very happy because you are starting to compute and can publish immediately a bunch of papers and so on. You will have 4 years. It's the time to do some weightlifting and study something that looks amazingly intimidating, where you don't see the boundaries of it, and it's a very fulfilling feeling when in a few years you look back and say, wow, this is amazing, the view from up here. And it's the time to do it in a PhD. It's a time when you have time. And once you do it once and establish this huge palace in your mind, then you become powerful and you can construct more in the future. But conversely, if you start with easy projects and then go on to hard ones, it's much, much harder. So I encourage you, go for something big that looks challenging and that looks very, very huge and where you are excited about, but which does look intimidating. So pick some hard topic. Okay, thank you. Yeah, and I have a T-shirt. Awesome. Thank you.
It's rare to encourage you supported the Canadian politics.
Ah, very good. Thank you. But you know, in São Paulo, if I use red now in the streets, I get kicked because it's from the party that there are strikes everywhere. So it's literally physically dangerous to use. And I'm flying there tomorrow. Yeah, there are news of people that got kicked because they were using red in Paulista. So I must be very careful, though. Questions? Comments or skeptical remarks? Yeah.
How does this non-unitarity show up in the final string thing?
This unitarity shows up in many places. It shows up, for example, in the fact that as you compute anomalous dimensions, they are not real. For example, they are complex. So you remember we used unitarity bounds to say dimensions should correspond to energy, so they should be real numbers, unbounded, and so on. And if you start computing anomalous dimension in this theory, they are complex, for example. Okay? Also, if you try to understand, forget about where it came from, but suppose we try to derive the Hamiltonian that would correspond to this spin chain by doing, again, two-point functions. But now you see the only vertex that connects a phi1, phi2 to a phi1, phi2 in the top, because of this cyclic order, it always takes a phi1, phi2 and flips it to a phi2, phi1. So the phi 2 moves to the left, right? So the only diagram connects A and B, where A and B differ by a particle moving to the left. It does not move to the right, it moves to the left. So what it will mean is that as you will start studying in your spin chain evolutions of particles, you will see that it's not unitary, and you will observe that, for example, phi 2s always move to the left, phi 2 daggers always move to the right, and when they hit, they get stuck and they stay. So you get non-diagonalizable dynamics and stresses and lots of fun things. But people did not start exploring that yet. I think it will be very interesting to do. More questions? Okay, if not, thank you for your interest and have fun next week.